Good evening. My name is Professor Crahor O'Brothy. I'm head of the School of Engineering at the University of Edinburgh. And it's my great pleasure to introduce our inaugural lecture this evening from Professor Pete Loftus, who is the Royal Academy of Engineering Visiting Professor of Instrumentation, Applied Metrology and Sensing. Pete has had a 40-year career in instrumentation and measurement. Most of this time was with Rolls-Royce, where he retired as Head of Measurement Engineering in 2018. We're very honoured to have Pete as a visiting professor here at the University of Edinburgh. He has a first degree in physics and a master's in Gas Turbine Engineering, and mainly focused on the application of measurement capability in high-integrity product design, production and through-life support. He did this work in a variety of contexts, from characterising material properties to on-wing inspection and machinery control and diagnostics. He holds some patents on innovative test measurement techniques. He now runs his own consulting business, as well as serving as chair of the Sensing Innovation Leadership Council. He's deputy director of the Research Centre in Non-Destructive Evaluation. He's past president of the European Virtual Institute for Gas Turbine Instrumentation, and through these, he continues to be a passionate advocate of the metrology discipline. I've had the pleasure of meeting Pete in person on 2 occasions, including this morning when he visited our new fast blade testing facility in Fife, and can attest to his passion and his interest in all aspects of measurement, metrology and sensing. And with that, I'm very pleased to welcome Professor Pete Loftus to give his inaugural lecture.
Well, thank you, and good afternoon, good evening. Good afternoon and evening to everyone watching remotely, and thank you very much for linking in. Thank you especially to those here in person. It's so disheartening trying to talk to a blank screen, so it's really nice to have some people here in the flesh, some real human beings. So, I don't know if this is going to be an unusual inaugural lecture. As a Royal Academy of Engineering visiting professor, I'm here to bring industrial experience into the teaching. So I'm not here to talk about a lifetime of technical achievements, or even to point to transformative technologies, though they will get a mention. I'm here to provoke reflection about this, what I think is an intensely fascinating subject of measurement and metrology. It's a subject that's fascinated me for at least 3 decades now. Call me sad if you like. Starting with the technology, then the quality assurance, trying to optimize technical strategy around measurement, and finally the discipline, the psychology and the people. And of course, as with everything else, it's the people that really bring the subject to life, and metrology is fortunate to have some very passionate and interesting people involved with it. In 2018, I had the enormous privilege of delivering a keynote address at the 22nd World Congress of the International Measurement Federation, IMECO. And there I was in inspiring and daunting company. The other 2 keynote addresses were from Nobel Prize winners. And it's really interesting, if you want a Nobel Prize in physics, then metrology is probably the field to get into. There have been more Nobel Prizes in physics for people working in measurement than anything else. So some really broad and deep science behind it. I, of course, have never come anywhere close to those lofty heights. But I have had a career that afforded me the opportunity of paid time to think about the fundamentals of measurement, how it's being used across countries, disciplines, organisations and cultures. And now to see it through the lens of academia too, which has been really interesting. And it's been a privilege to rub shoulders with the inspiring men and women who lead international metrology and the enthusiasts that the subject just seems to bring from all disciplines and walks of life. So, why does measurement fascinate me? And lots of reasons. The diversity is one thing. Whatever area of science you touch, then it's got its measurement history and its opportunities and so forth. The way it touches all of our lives, we can't get through a day without touching on measurement in some form, whether it be in the kitchen or in the pub or wherever it might be. The ways it can be misinterpreted, the way we think we're all talking the same language when we're using results of measurement and yet interpret different things. And we've seen that in spades through the pandemic, where communicating measured results, whether it be lateral flow tests or temperature tests or whatever it might have been, and what that meant to the public has been a bit of a nightmare. The psychology, the way we interact with measurement as human beings is endlessly fascinating. And the fact that different disciplines approach it in many subtly different ways. It's also got some really great quotes, and there's one there from Plato. He was particularly prolific in coming up with good quotes about all things measurement. So I went into measurement believing it had all the answers, and I think I've progressively learned some of the questions to ask of measurement. I think I've glimpsed a little of the opportunity before us and hope to offer a few pointers to the future of measurement application. Greater minds than mine have observed these things, and greater minds will provide the answers. But I stand before you as one searching to draw together some of the threads of this really fascinating story. So I'm going to go through a little bit of history. I'm going to talk a bit about the nature of measurement. I'm going to talk about the scope of measurement and metrology, what it's achieved, and then spend quite a bit of time thinking about what's left to achieve. What can and should we be doing for the future? And finish up, since we are an engineering school after all, finish up with some of the technology and the impact that could have. So my purpose in the lecture is to remind us of where metrology stands today, the opportunity we all have to help build confidence in real-world data. So, to the history. And you don't get away with a lecture of this sort without something from ancient Egypt. I don't think they actually looked like that back in those days, but there's clearly some kind of weighing going on there. I suspect the guy on the left is trying to collect taxes, because that was usually what they did weighing for. So from the earliest of times, there was measurement going on. There's a quote there from the Magna Carta, signed by King John in 1215. Sorry, I couldn't find anything Scottish, but of course the Magna Carta was the Declaration of Independence of its day. It was the highest document in government, and there, along with all of the other wise words, were things about standards of wine and ale. They got their priorities right in those days. Corn, cloth. I'll leave you to do some homework on what an L was. It's about that much. And weights in there as well. So as humankind began to trade and make structures, measurement became absolutely a vital tool. And measurements were a focus of rulers and governments from earliest times. So it wasn't just geeks in white coats, but actually the rulers realising that you can't run an economy or collect taxes without a measurement system. So governments, of course, set about helping their citizens to achieve consistency in the measurements taken. And there's an example there of City Hall in Germany, where they've helpfully put some length scales on the City Hall. Presumably the citizens would go up and compare their scales. It's a way of doing traceability. So the government was there getting involved, promoting better measurement. And as usual, when governments help, they seek to compel. And so it was with measurement. So if we trace the lineage of those early beginnings, we arrive at the modern domain of legal metrology. Legal metrology has its own international framework, the OIML. So some measurements under the scope of legal metrology are controlled by the state. How to measure them, the units to use, the calibration and maintenance practices, all laid down. And those are usually things that directly impact the consumer or trade. Petrol pumps, grocer's scales, if you can find a grocer's scale these days, water meters, those kind of things. So what about measurement that's not in the scope of legal metrology? Well, that's not illegal metrology, as you might think, but scientific metrology. And so given this long history of state regulation, personally I find it remarkable that there's so much of measurement is unregulated. And those of us working in science and engineering will seldom come across legal metrology. In fact, many people I talk to from our disciplines have never heard of it. They're not necessarily conscious of trading standards officers coming around checking all of these things. But I am free to, and we all are free, to do whatever we will with measurement. We can invent new units, methods, calibrations, whatever we want, from a legal point of view, which I find quite interesting. So I could introduce a unit of, the Loftus unit of verbal incoherence. And we could rate this lecture in Loftuses, or kilo Loftuses maybe. Or if it was really, really bad, we could do it in Peter Loftuses. Sorry. There are not many jokes in metrology, and you can see why. But with that great freedom, as someone said, comes great responsibility to adopt valid approaches so that others can trust our work. In science, the state doesn't check your equipment or methods, nor in business to business. But of course, it's not quite the Wild West out there. There are standards, and those are imposed by contract where needed. But it's done in silos of discipline and sector and so forth. And it's not governed by metrologists, it's governed by people who want to get their business done. Quite an open space there for people to operate in. All right, so I mentioned the nature of measurement. And I found myself spending some time talking to students about this. That measurement has an uneasy association with truth and confidence. So for some, a measurement implies truth. For some, measurement is equivalent to judgment or steady progress. We talk about measures of happiness, about taking a measured approach, about measures being taken to prevent injury. It's also closely linked to action, as in the phrase, what gets measured gets done. So in everyday life, we have this very broad notion of what measurement might be, and we blindly assume that instruments are true to as many decimal places as the scales allow. As metrologists, we need to deal with a more precise interpretation of measurement. And unfortunately, there is no name that I've ever come across for that sort of measurement. So in measurements of that type, we're obliged to state not only the measured result, which is an estimate of some true unknowable quantity value, but also our estimate of the uncertainty, i.e. to express our confidence that the true value lies within prescribed limits of our measured value. In industry, measurements are only ever made to inform decision making. But without these uncertainty estimates, those decisions become gambles. The use of measurement uncertainty is actually still in its infancy, and in fact, uncertainty in general is in its infancy in terms of the way it's deployed. But what's happened is our gambling strategies have been refined over the years to implicitly take account of assumed levels of uncertainty. We call this engineering judgment. My advice is to be very suspicious of engineering judgment and check it with data. As Deming said, in God we trust, all others must bring data. So if you're making a judgment based on some test results and you've not checked all of the things that went into that result, did somebody change the instrument out halfway through the test? Did it get recalibrated? You can't expect to make judgments about those results without that kind of insight. We shouldn't expect it. So the phrase that I try to impress on students is that measurement is a process of estimation. I think that's the best way to think of it. But the scope of measurement itself is an ambiguous one. The concept of measurement is an ambiguous one. Magna Carta standardised currency at the same time as it did measurement units. But is accountancy in scope? William Shakespeare's measure for measure also refers to the legal concept that is central to the play, that when a person commits a crime or sins, he or she should be made to pay, either by making some kind of restitution or suffering an amount that's equal to the suffering he or she has caused. Measure for measure. I find that metrologists will often retreat into measuring the thing they can measure and leave the messy business of estimating the thing that we really wanted to know to someone else. And I think that's unfortunate, and in some ways leaves society the poorer for it. Perhaps a more technical answer to that question about what is the scope is this example for sensing, what's become known as the sensor stack, which takes you all the way from a measurand to some actionable information. I quite like the phrase actionable information as the output of a measurement process. And of course you're adding value all of the way up that stack of activity. One thing I would note, and I'm sure you'll agree with me, is that the top half of that stack is receiving a lot more attention today than the bottom half of that stack. And of course it all has to work to get the results. In some ways, the most significant step is the one at the bottom, the coupling to the measurement. So if you're interested in where's the uncertainty in a measurement process, that's not going to come from the communication and networking and the analysis and so forth in the main. Most of the uncertainty tends to come from that coupling to the measurement. So it's relatively straightforward for me to tell you the temperature of a thermocouple bead that I hold up in this room. Determining how the temperature of that bead relates to the temperature of the air in this room is a lot more difficult and a lot more subject to uncertainties. So the areas that we focus on in that stack are not necessarily the ones that have the most impact, at least in terms of functionality in that way. But it's an answer to the question. If we were to start to produce a taxonomy of measurement applications, there are lots of ways of doing that. You could look at where it ties into a wider process, such as the product life cycle. And the answer to that is everywhere. It's right throughout the life cycle of a product. Or you could look at the function it performs, a taxonomy that I tend to prefer. You could look at, is it there to provide control? Is it an input to a control system? Is it there to provide monitoring, inspection, conformity assessment, diagnostics, or experimental? So they're all, in a way, different questions of the measurement system. Interestingly, the first 4 are actually control. They've just got varying degrees of human being in the loop. But whichever way you choose to draw a taxonomy, it's clear there's an awful lot of it about, and it's awfully critical in lots of ways. So I said I'd talk about achievements, and there are so many, it's hard to know where to start. So I've just picked one. And I think the SI system is not only the crowning achievement of metrology, but in a way, the crowning achievement of civilization. The fact that we've got the entire world to agree on this system, that means we can all trade and communicate and do science together on a level playing field. And that we've got almost every country in the world supporting and operating this system is quite remarkable. I can't think of anything else equivalent to that. And we tend to think that it's been around forever. I always used to think it's been around forever. It is actually the same age as me, which makes me sound really, really old, which I am. But yeah, 1960, the SI system came into being. It, of course, built on previous work. So the Meter Convention was signed by 17 nations back in May 1875. And that was really the start of the international journey of metrication, if that's the right word. And we still celebrate that signing of the Meter Convention on the 20th of May each year with World Metrology Day. Not a lot of people know that, but we do. And each year there's a theme for World Metrology Day. This year it's Metrology in the Digital Era, which seems pretty appropriate given the impact that all things digital are having on metrology, and that metrology is having or trying to have on all things digital. The two are deeply connected. Unfortunately, we didn't manage to contrive for this inaugural to be on the 20th of May, but we're not too far off. But the SI is not static. It continues to evolve, and 20th of May, we keep choosing this date, 20th of May 2019 saw one of the biggest changes in its history when the last physical artifact was removed to form a coherent system of units that can be realized anywhere in the universe. That's quite mind-boggling. But so no longer do we need that lump of platinum iridium in a vault in Paris. Everything is defined in terms of fundamental constants. I don't have time to go into that story, but it's a really fascinating tale. And whilst it sounds really dry and dusty, the passion that went into getting to this point was phenomenal. Trying to arguments about the mise en pratique, how it's going to be realised, trying to get the right values for those constants. it's been very cleverly contrived that nothing changes. No one's noticed that this change has taken place. But we've done it, and that just strikes me as being an awesome achievement. So the SI has been a real unifying journey. And people are coming together, of course, in terms of the application of measurement as well, in all kinds of disciplines, too numerous to list. But there, I think the rosy picture ends, because the application of measurement is needlessly different across those disciplines. And in the sense that Deming described the cost to a business arising from lack of standardisation, that lack of standardisation costs all of us. And it contributes to the misunderstandings between disciplines, between scientists and the public. The fact that a lateral flow test the performance of the test is described in a different way to trying to detect disease by measuring the temperature of your forehead. Not that that ever was a good idea. So there's an opportunity there to adopt a more common approach. So that brings me on to how could metrology do even better? And I'd like to break that into four areas: process clarity, discipline recognition, partnering with other disciplines, and some technology. So let's start with the process. And I'm quite a big fan of quality systems. That sometimes gets me askance looks, and it just got me a couple in the audience. Yeah. If not outright hostility. Intelligent people tend to hate quality systems. They value the intellectual freedom, and they don't want to be told what to do. But the analogy I always use is the pilot, the aircraft pilot. They all have a checklist. You have to go through the checklist before you even start the engines. And they're not stupid people. They do it to make sure they don't forget things, and they get it right. And we're all grateful for it. And so that's the way I view quality systems. It's a framework to help make sure we get things right. And so what you see there on the slide is the kind of thing I mean by a measurement process that could form part of a quality system. If you control the way you do those things, you'll get a successful result. And you can mentally run through. I tend to do it when I'm doing DIY at home, and because I'm sad. But you can do that in seconds, or you can spend years doing it for a really complex system that's taking a long time to design. But it gives you that framework and that checklist. And the value of such procedures is, I think, in the decision gates, so the steps between the steps. So you can mandate checklists, you can mandate who is going to make decisions, you can mandate the training that they need, the competence they need to make those decisions. And the extent to which you do that depends on the criticality of the business you're working in and the decisions being made. But it gives you a framework. I think performing metrologically traceable measurements correctly and taking them into new areas of capability demands an attention to process that has been lacking up to now. The generic guidance on process in international and national standards is far from comprehensive. And we're left to decide what to measure, how to measure it, how to validate the system, how to analyse its performance, and how to state the results in isolation, working in different disciplines. And that unnecessary diversity of approach is both economically and scientifically damaging, I think. So I just wanted to pick out three examples, the asterisks on that slide. So if we begin with the first one was the ensure a capable measurement system. Seems like a good idea, isn't it? Make sure you've got a system that will work in the first place. And there's a lot you could say about that step. It's obviously a fairly fundamental step. The point I wanted to make was that right at the beginning of that process, you have to decide what you're going to measure, as well as how you're going to measure it. And that is an opportunity for some reflection. Here's just an example from earlier in my career. I'm rustling. I don't know why I'm rustling. Anyway, so if you are interested in, as I used to be, the lifetime of a blade in a piece of turbo machinery, an aerofoil, then you're going to be interested in the maximum principal stress in the component. That is pretty much impossible to measure because it's underneath the surface, you can't get to it. So what people do is they either measure a strain on the surface or they measure the tip deflection. And they then use a finite element model to relate that to the maximum principal stress in the component. So my question is, which is the measurement? Which is the measurand? To me, it's unhelpful to redefine the measurand as surface strain or tip deflection because those are the things we can get at. What use is it to know the uncertainty in those things when we actually want to know the uncertainty in the maximum principal stress? So there's some soul searching as well as technical reflection around what it is do I want to what is it that I want to measure and how am I going to measure it? I think the other takeaway from this example is it becomes increasingly meaningless to separate measurement from simulation because the two have to work together. It's hard to buy a measurement system that doesn't involve some kind of software and includes some element of simulation. The connection between measurement and simulation, I think, just becomes ever more intense as systems evolve, and the two just have to be treated in most cases as part of one whole. So that brings us to the second asterisk, which when I first wrote this I called check you've got a calibration. And I now prefer to call ensure a metrological control, which has the difficulty that people say, what does that mean? But we get over-obsessed, I think, with calibration. So we must always calibrate instruments, except when we don't. So in space, long lifetime products, depths of the ocean, as we were talking earlier today, when it's not affordable. There are lots of occasions when we choose not to calibrate. And a lot of the time that's fine, if we've taken a conscious decision. The goal is metrological control, confidence in the measurement process. And calibration is a tool to deliver that. But we shouldn't become a slave to it. Universities own thousands of pieces of sophisticated measurement equipment. Should it all be calibrated? Should the user take responsibility? I think you need to decide these things on a case-by-case basis. But the economic answer is not always calibrate everything. So finally, on the process, I'll just pick up on the last of these asterisks. On estimating performance. And I've always advocated you should always estimate the performance of a measurement system before you make it. So don't go spending the money on it until you think you're capable of doing what the measurement system sets out to do. So you estimate the performance, make it, and then validate it. But what does the performance of a measurement system mean? How do we describe that? Well, metrologists have focused on building confidence in data, I think, longer than any other discipline. That's been the core of what they've tried to do. And the good news is a thing called the Joint Committee on Guides in Metrology has produced an extremely comprehensive and respected guide on how to assess and report measurement uncertainty. The bad news is that many disciplines don't use that guide, and that it's, in any case, only a partial description of performance. And I wanted to highlight one particular area, I think, where it falls short in terms of not being comprehensive. Because measurement uncertainty analysis assumes that the measurement system is conforming. So there are no faults and no mistakes. In reality, of course, that's not always the case. And we have to account for the possibility of non-conformance. So if we're designing a safety critical system, it's not sufficient to know that 95% of the time the true value will lie between given limits. Because 5% of the time we might be killing people. We have to know the worst case extremes of what might arise, and we must reduce their probability to a negligible level. At the other end of the scale, we might have a very low criticality system, such as we might use in an experiment, but there are so many process steps that the probability of error failure is parts per dozen rather than parts per million. In general, the more important something is, the more we should pay heed to integrity. The more demanding the requirement, the more we should pay heed to uncertainty. Unfortunately, in industry, we have many problems that are both demanding and important, necessitating attention to both. And there isn't actually a consistent framework in which to do that today. And that performance of the measurement system, once we've estimated it, it needs to be managed both before, during, and after the measurement itself. And I've worked in the past on ideas around how you do that in a consistent way. But what we're talking about is putting metadata to the data. So we have a measured result, which is the data, and we need to couple that with metadata that describes uncertainty, integrity, and other aspects of context. So we might add things like relevance, perception, cognitive bias, depending on what it's for. Then there's context that is important to it and needs to live with the data. So those are just three elements of the measurement process that I think are often neglected and offer opportunities for improvement in all kinds of walks of life. The next question, I think, is, well, who makes all of that happen? And so this is where we start to think about measurement as a discipline. Industry seeks to hold people responsible for the validity of measurements. Businesses stand or fall by the measurements made on their behalf. But there's really no consistent definition of the competence required to execute such a role, let alone how to demonstrate it. And that is starting to receive attention through a few international efforts, including the UK's National Metrology Skills Alliance, which was actually launched 2 weeks ago. So, up to the minute stuff. What about academia? So who's responsible for the metrology? Is it the technician who gets the instrument calibrated? The student who does the work? The PI? Peer reviewers? Personally, I find it hard to feel confident about that chain. Sure, most of the time, it is absolutely fine. But if you really ask me if I'm going to stake my life on data produced in scientific papers, I'm not so sure. So, should there be a widely recognised discipline behind the application of metrology? How many of the general public know what metrology means? Does Alexa understand the measurement process? Other personal assistants are available, but let's see if this works. Alexa, what is the surface area of the British Isles?
The British Isles area is 488,497,400,000,000 square inches.
Thank you. And what's the uncertainty in that estimate?
Sorry, I don't know that one.
So why square inches? I have no idea. But it's just not a common question, obviously. Otherwise, Alexa would have known the answer. So at all levels, we have work to do, I think, in terms of building a better understanding of metrology. There certainly is a discipline of metrology, but often only recognised amongst suppliers of metrology equipment and services. An analogy I often use, again, it gets things thrown at me usually, but if I use accountancy as an analogy, then we have rule setters, we have rule followers who are chartered and certified to do so, and then we have dabblers like me who can do bits and pieces but don't really know the detail. But there's a common thread through all of that. And in a way, that common thread doesn't exist in the same way for metrology, which I think is unfortunate. Another example is statistical engineering, where, like metrology, there's a clearly defined science, but its application has been in disparate sectors and disciplines. And there are moves to create a discipline around statistical engineering. Quite analogous, I think, and motivated by similar arguments. Personally, I think metrology is too good to be left to metrologists, and that value chain needs to work and affect all of us. I found myself already at the university not teaching a well-founded framework of methodology to deliver sound metrology, which is what I would like to be doing, but more encouraging students to question. It's always important that students question and keep an open mind, but if they were doing so in the framework of an established framework, then that would be a much easier sell, I think. And this working together across disciplines, I think, becomes really important. And it's quite interesting that the sort of disciplines who are big users of measurement are also the disciplines involved in the measurement process itself. So the coupling between those disciplines is really interesting and key. But the fact that all of those disciplines are involved also contributes to that slight lack of clarity about what the discipline of metrology actually is. If I think of that more in terms of sensing again, then we can see that the sensing system forms part of at least three other systems. You've got the physical system, the motor vehicle, washing machine, whatever it might be. You've got the digital system, receiving and using the sense data. And you've got the metrology system, ensuring that data validity. And And of course we have specialists working in all of those areas, but we also need some people that are working across them all and doing the integration so that we can deliver integrated solutions. I'll just pick one example of what I've called cognate disciplines. People working in simulation. In my working career, we've gone from a paradigm where experiments were performed as functional evaluations, and then numerical simulations were used after the event to understand the behaviour we'd observed. And now we've moved to a paradigm where the numerical simulations predict performance and physical experiments provide the necessary data to validate the models. And a measure of the quality of a digital twin for me is whether you measure cause or effect. So if you've got a really high quality, let's start with a low example. If you've got a really low quality digital twin, then you need to measure the effect, you need to measure the outcomes. Because you don't trust the model. If you've got a really high quality model, then you can focus on measuring the inputs and the cause rather than the effect. Whichever way you do it, it's clear that those two things have to come together a lot more closely. So there are opportunities to do better in linking not only that example, but all of these cognate disciplines. And the lack of integration across such disciplines has, I think, worked to reduce the impact that metrology has in the world, which is a shame. I said I'd get onto technology. So with technology and methodology, where could we do better? And I think starting to see beyond the silos is an important start. So the diversity of applications makes it difficult to know where to focus. But there are some areas of focus common to all measurement applications and some which address very broad classes of application. So the things that are kind of common to almost every measurement that you point at are these questions around how do you estimate the performance, the uncertainty, the integrity. Some of the sensing technology, it can be generic. The process, the discipline, the kind of things we've been talking about. All of those things can be really very generic across different domains. If you're working in conformity assessment, you've got questions around the decision rules and increasingly how do you embed those in AI? How do you make those decisions? If you're working in the world of experimental, we've just talked about fusing test and simulation. And all of that becomes key. If you're working in control and monitoring, then the integration of sensors into control and monitoring systems becomes important, and there are lots of generic issues to be resolved there. So there are things that we can do that will benefit sensing across and measurement across a whole raft of disciplines and applications, and it would be good to focus on some of those. So what about the technology itself? How can that impact measurement? Well, some of the pull on measurement technology that I've been very conscious of through my career are things like these. So people talk about the reduced reliance on inspection. People talk about inspection being non-value added, that the process should deliver conforming product without inspection. Well, that requires the measurement process to move upstream, get kind of down and dirty with the process. And there's a whole new set of requirements to be addressed there. The reduced margins point, so more accuracy is being sought pretty well universally because that can lead to efficiency gains and better performance. Adaptive and autonomous products of course, bring their own demands, and higher integrity is part of that. The proliferation of digital twins means better understanding of the validity of those digital twins, grounding it in reality through sensing and measurement becomes more and more important. Better prognosis through life. You need to know when things are going to happen. If you've got a product in service, you need to know when it's going to require maintenance. You need to know when food's going to run out in the fridge. All of these things, people are demanding more insight about the future. And that involves better measurement to be able to extend the lifetime of the prognosis. And then extreme conditions where, if we want to sense everywhere, then some of the places we need to sense are more difficult than others. So numerous demands on better measurement from industry, and metrologists, of course, well placed to address these if we create those opportunities for them to do so. I just wanted to highlight three areas. I mean, you could highlight so many, couldn't you? But three areas of technology that I think are really pertinent. As the title of this year's World Metrology Day suggests, all things digital having a major impact on the way measurement is used. The thirst for data doesn't wait for metrologists to validate and calibrate systems. If a data source is available, it's put to use. So building confidence in those data after the event is a major challenge. And it feels to me that metrology is currently on the back foot with that trend, and it needs to be leading the fusion of multiple data sources and doing so with appropriate metrological control. The density and sensitivity point, sensing becomes ever more dense, both in temporal terms with higher bandwidths, being sensed, transmitted and processed, and spatially with miniaturization and connectivity, driving more and more dense networks of sensors. And all of that information drives an improved connection with the physical world, but only if we can extract information from that data with confidence. And the final area I wanted to highlight, which probably gets a bit less attention, is quantum science that is opening up transformative capabilities that I don't think we've started to recognise properly yet. So quantum metrology, much of which is behind the new SI, means that national measurement labs don't have to be the source of traceability. Realising the SI anywhere in the universe means you can realise the SI in the factory, or in space, or at the bottom of the ocean. So how can we cache that in? Well, you might be able to cache it in terms of ultra-stable measurement systems, or you may be able to cache it in simply in terms of efficiencies without having taken away that traceability chain. It remains to be seen how we best cache it in, but it's potentially transformative, I think. Quantum sensing offers orders of magnitude increase in sensitivity, certainly for things like magnetometry and gravitometry, magnetic and gravity field sensing. And the ways we can cache that in are still anybody's guess as yet. But it is such a big orders of magnitude leap in sensitivity. And actually in two parameters that are very difficult to shield for. So it's hard to stop gravitational waves or magnetic fields. So what insight can that provide for us? People are still thinking that through. Quantum imaging, where we start to exploit the fourth dimension, time, in sensing systems, brings these people have called spooky possibilities of seeing around corners or through fog and so forth. So that whole realm of quantum science is I think really quite exciting in terms of the metrological capabilities it might deliver. Exploiting all of those opportunities is going to require a much wider and deeper metrology skill set. And in a very small way, that's something that my visiting professor appointment is intended to start addressing, starting to tease away at what the skill set should be and how do we develop it. So to wrap up, we've seen that metrology has come a long way, and we've seen that it underpins our modern world in so many ways. We've also seen that metrology still has huge opportunities to develop further, and that realising those not only requires technological advance, but also requires future generations to learn, work and organise in new ways. Of course, we're only granted an imperfect view of the future, but we need to use that to equip future generations as best we can. We can either continue to develop metrology in silos of discipline, industry and culture, or we can take inspiration from the SI system itself and build a framework of measurement application that is generic and well understood. So I'd like to finish by urging you to invite a metrologist into your life and become part of that collaborative future of confidence in data. Thank you. Happy to take questions.
Thank you very much, Professor Loftus, who is a metrologist that I invited into my life 5 or more years ago, not realising what I was letting myself in for.
Regretted it ever since.
We should start, now that Professor Loftus is finished, by inviting questions. We can invite questions from the audience in the hall. And I believe, Louise, we can invite questions from the audience online.
I've not got any yet.
Okay, so please. All right, we've got an enthusiastic front row, and now I'm going to bring the microphone to you so that the folks who are online will be able to hear.
Hi there. Thanks for that. That was really interesting. I'm going to sort of precede this by saying that I come from an earth science background, where I know that when we're trying to interpret, say, some resistivity values geologically, there's some quite wide ranges. So any uncertainty is kind of swamped out by those. And that leads me to sort of ask what in your opinion, how much should we be incorporating metrology into academia when sometimes we have measurements that might give results that we have to interpret quite qualitatively? Like, do you think we should be pursuing it more in the undergraduate stage and kind of giving them more information and importance there? Or should it be taken to, say, the peer review stage where calibration documents are required for publishing, for example? Sort of where do you think we should be sitting in there?
Well, personally, I mean, perhaps you'd expect me to say this, I think all of the above. And starting in primary schools, you know. So in another life, I'm a scout leader, and we've taken some of the youngest Boy Scouts, the Beavers in the UK, out measuring the height of trees with a stick, you know. And it all helps to build that appreciation of what metrology is all about. So you can start there, and I mean, one of the things I'm really fascinated to work on is there's a ISO standard about how you do metrology in industry and how you control metrology. And I'm really interested in what's the equivalent of that. By the way, that doesn't necessarily work very well in industry, but what's the equivalent of that in academia? Because you can't do it in quite the same way. You can't say there's this guy in the corner we're going to invite in to to oversee your measurements. But that's not to say you can't do anything at all. So I think there's opportunities throughout the scale of higher education, if you like.
Thank you, Pete. It was an excellent talk. Thank you very much. I think my question is similar in around the skills landscape and just really asking your observations on how that landscape has changed in the time that you've been working and how employers are maybe changing their approach. Are they doing more CPD for metrology, or are they taking in consultancies, or how is that approach being embedded into an industrial setting?
So I think most people involved in industrial metrology would say not well enough yet. I was fortunate to chair, well, remotely chair a session at the CIM conference last year, where we were discussing that very thing with people involved in metrology from all kinds of different industries and disciplines. And there were a lot of interesting consensuses that came out of that. But the need to start early, the need to embed metrology in process, the need to be more consistent about the way we qualify metrologists were all, common themes that came out of that discussion. So it has changed, and the move towards ISO 9000 style quality systems has in some ways accelerated that. But it hasn't always in every area, because you can, those systems are only as good as the thought process that goes into interpreting them for a particular industry or discipline or whatever.
Pete, we have a question online now, so that the folks who are viewing remotely don't feel left out, I'm going to read that out. And it's from Abbas Rizvi. And the question is, other than condition monitoring, how prevalent are in situ metrology in production systems?
Apart from condition monitoring.
How prevalent, let's say, is in situ metrology in production systems?
So I take that to mean we're putting on one side using measurements to monitor the health of the process, and we want to use the measurement to monitor the process itself. So bringing inspection into the process. And I think the answer to that is it's very much in its infancy. It's one of those things that certainly for 15, maybe 20 years, people have been talking about the need to get away from inspection and embed measurement in processes. But it's easier said than done. And in a way, it's second order priority, because you've got to get things right first. And then once you're under control, you can start to move in that direction. So I think that's still in its infancy, but a lot of fascinating careers to come, I think, in that area.
Okay, we have a question over here, so just give me a moment.
Hi, Professor. Thank you for your lecture, first of all. My question is about the quantum measurement thing. So, well, correct me if I'm wrong, but when you're observing in the quantum realm, then you're changing the outcome, basically, of the measurement. So how can we see in the future that we're able to apply metrology into the quantum mechanics?
Well, I don't think we're going to circumvent Heisenberg. Metrology is already there in that metrology is extensively applied in understanding the quantum world. I was more focusing on what the quantum world can do for metrology, but both are certainly true. And I don't know. Does that answer your question?
Yeah, I think so. Yeah.
I'm aware of the time, and we do need to move to the reception. I'll just mention to folks who are in the hall, we'll leave by the back doors because the reception is upstairs. So, but before we do that, I'd like to propose a vote of thanks. It's been a very interesting, fascinating evening so far. I liked the Plato quote, but I have a riposte from a not quite philosopher from closer to home, but Lord Kelvin. And this is a quote that I use in one of my own lecture courses. Lord Kelvin's said, "I often say that when you can measure what you're speaking about and express it in numbers, you know something about it. When you cannot, then your knowledge is of a meager and unsatisfactory kind." And that's how I start one of my own lecture courses. I would like to say, by the way, I mentioned previously that I first met Pete more than 5 years ago. There was a centre for doctoral training shared between University of Glasgow and University of Edinburgh, whose title was CDT in Integrative Sensing and Measurement. Who better to invite onto our advisory board than the head of measurement engineering of one of the UK's most prestigious companies, Pete? He joined our CDT and was instrumental in improving and helping us to make the training program more focused for those PhD students, who included physicists, chemists, and a range of engineers. As we reached the end of the final cohort, Pete and I got to talking ourselves and Andy Harvey, who was the director in Glasgow, about what we could do, because we didn't want to lose contact with Pete. And I was aware of the Royal Academy of Engineering visiting professor scheme. We had a previous visiting professor in systems engineering, Professor Colin Cunningham, and Pete and I together cooked up the idea of visiting professor in instrumentation, applied metrology, and sensing. And Pete's been doing that now for about 18 months. I think we're about halfway, I believe. And he mentioned himself, it's not so much about introducing a 10 or a 20 credit course in metrology. It's about embedding the principles of good measurement in the way the students think from year 1 to year 5. And that's the way it's been working. Tonight, Pete, you have really lifted our heads, I think. And I believe that engineers spend too much time in the trenches, keeping their heads down, solving today's problem today. I think what you've done for us today is you've taken us out the trench to the top of the hill, and we've surveyed metrology from a high viewpoint, which has been extremely helpful. You taught us a little bit of history, a little bit of law, a little bit of philosophy, a little bit of ethics, and psychology and methodology. And that's another thing. Sometimes we can be too narrow as engineers. It is good to think more broadly. Just out of interest, I'm going to look for a show of hands here. Who before this evening had heard of W. Edwards Deming? One or two folks. You know, for me, he's like the Richard Feynman of metrology. You could do no better than read his autobiography or go read one of his books. I teach him in third year here, as you know, because Pete's looked over my lecture notes. He was one of the engines behind the economic efforts of the USA in World War II. And if that sounds a little bit too destructive, Douglas MacArthur took him out to Japan at the end of the Second World War, and he was instrumental in rebuilding the Japanese economy. An engineer, a metrologist. Fantastic. So tonight's lecture has given us a flavour of Pete's visiting professor mandate in his 3 years. I enjoyed it. I was fascinated by it. And what I would say to you, like me, if you have a measurement problem in future, you will know who to go and ask. So thank you once again, Pete Loftus.
Thank you.